Hello. That was a short coffee break for this room because we started a bit late. But now we're back on schedule. So next one to present is Dr. Georg Lukas, and he will show us about Java SSL Socket, or how bad APIs can do really bad stuff for you.
Thank you very much. Hello, my name is Georg Lukas. I'm here for showing. Is it okay? Okay. A little problem which many application developers happen to stumble on when they write networked code and try to achieve something secure in the way. First, a little bit about me. I'm an IT security consultant working for a German consultancy. My focus is not only IT security, but also mobile, smartphone payment is one of the focus points. I'm an open source developer. I started out with different embedded Linux projects and settled on Android eventually. And this is also part of why I'm here. I'm the maintainer of Yaxim, yet another XMPP instant messenger. You can see a screenshot on the right of the slide, which is an open source XMPP client application. And recently I also started Yax.im, which is a public XMPP service which can be used by anybody and which is tightly integrated with the Yaxim application. And the Yaxim application is also basically the reason I'm here today, because when I wrote code for it, Yaxim is using XMPP, XML-based communication protocol, and it is using the TLS network encryption protocol for securing the connection to the server. Yaxim is using the SMAC library for XMPP and the Memorizing Trust Manager module, which I have developed. You can see a screenshot on the right again, for ensuring TLS connections. And I was writing a hostname checking module in MTM, and when I tried to add that hostname checking module into the SMAC library, I realized there's no place where I could add it. And the reason for there being no place for it was because SMAC was vulnerable to man-in-the-middle attack because it didn't perform any kind of hostname checking. And the problem why it could happen was because of how the Java API is designed and how it doesn't show its users the problems they might have when trying to write secure software. So what I'm going to talk about today, I would like to start with a brief history of SSL and TLS, then demonstrate the different APIs which are available in Java, and from there I would like to build up how you can make your Java or Android application more secure. And finally I will give a brief outlook on what can be done after we have seen what kind of attackers we have to work against. It all started in the early 90s, where we had the Wild West internet. Everybody was using insecure protocols, Telnet, RLogin, FTP, NFS. There was no authentication. When you had access to a machine, you were either administrator, which there were not so many of, and you were trusted anyway, or you were just a user and couldn't do anything evil anyway. In the mid-90s, Netscape started out with an encrypted end-to-end communication protocol they called Secure Sockets Layer. It was released in '95 as a specification in the SSL version 2.0. And 1 year later, it had to be redesigned because of a bunch of security problems it had inside. What Netscape publicized as SSL 3 was later on rewritten as an internet request for comment document, which is a typical way how you document internet and network standard protocols. It was released as Transport Layer Security in 1999. And based on that, in 1999 and 2000, different application level protocols like HTTPS were also specified as, you take a protocol you had already, you put it over TLS, and then you have a secure communication protocol. And there was already a distinction being made. The Transport Layer Security Protocol only handles the connection encryption, but the verification of the endpoint, like the hostname check, which this talk started about, had been done at the application level. In 2001, Sun, which is now owned by Oracle, created a library for the Java software development kit to provide encryption. It was a Java Secure Sockets extension library. It was released with the JDK version 1.4 and was also made available for the earlier versions. And it was basically based on the 99 and 2000 protocols. Then for a while, nothing of really big importance happened. And in 2006 and 2008, updated versions of the TLS protocols, 1.1 and 1.2, were published. They were fixing theoretical problems which since have been proven to actually exist and be exploitable in 2011 and in 2013. There was a bunch of other attacks which I'm not going to show in detail because you can read them up, and it is already hard enough to write proper TLS even in absence of these attacks. In 2011, finally, SSL was deprecated. However, not all of it, but only the really, really broken SSL version 2, which had been known to be insecure for 15 years. So you can see that the deprecation of protocols is lagging behind the state of the art a little bit. Also in 2011, a major milestone of the specification was created. The RFC 6125 was written down, which provided developers with instructions on how to properly secure remote connection and how to verify if the host name of a connected server matches the certificate presented by the server. That RFC was named, maybe a little bit clumsily, Representation and Verification of Domain-Based Application Service Identity with an Internet Public Key Infrastructure using X509 public key infrastructure certificates in the context of, we are nearing the end of the title, transport layer security. The people who wrote that RFC, I have asked them, and they couldn't quite remember what the reason for the exact name was, but they told me they're calling it just Third ID. So this is a very important document for people who are trying to write TLS implementations. Yeah, in 2012 and 13, further attacks were demonstrated. Now in September of this year, the Poodle Attack has been demonstrated. Maybe some of you heard about it. What it does is basically to attack the SSL version 3 protocol, and it is now actually considered really, really insecure. Don't use SSL version 3 anymore. And my personal problem with it was that you often see something SSL in the subject lines of news or documents. Don't do it anymore. Or you also see, like in the title of the slide, SSL/TLS. Don't use that either anymore. Just stick to TLS. It's the only standard which is still usable now. So if you want to implement TLS, how hard can it actually be for a developer? How hard is it to make secure communication? Now there's a bunch of little challenges. One of them is, if you get such a certificate, you have to check if that certificate is actually valid. It has a validity time, which is pretty easy to check, except if your time clock on your machine is set off, and then you get strange certification errors you don't quite understand. The other problem with a certificate is if it is signed by a trusted certificate authority. There's a bunch of the trusted CAs out there, and you know there are some which are more trusted and some which are less trusted, but essentially it boils down to what is integrated in your operating system or in your browser suite. If you have ensured that the certificate is okay, more or less, you have to check if the host name you connected to and the certificate integrated host name actually match. So do you really get the certificate from the server you try to reach? Then another challenge which is especially important for application developers is to have some kind of switch in the application. When you are developing, TLS is usually more of a problem than of a solution. You try to connect to your server, but something goes wrong, and it is not really easy to get a certificate for something like w3dev.intranet or local IP address or some other non-public service. So usually application developers add some code into the application to allow it to work in development mode and later on forget to remove it for production, shipping insecure software. And then you have, recently in the last years, people who started to run their own server infrastructure, like get your Raspberry Pi connected to your DSL box, install some PHP-based private cloud software, and have your fun with it. And such installations tend to have very interesting certificates on them. It starts out with self-signed, and sometimes you have expired certificates because the administrator just didn't care about updating it or even didn't notice it expired. You have certificates which are issued for one host name, but you want to connect to a different host name, maybe on the same domain, maybe on a different domain. And if you are writing software which has to connect to different user-provided servers, you need to care and to take care of it and can't just disable security at all. So if you want to achieve TLS connection, there are different Java classes. One of them is the Ssl Socket class. It is basically a regular socket which, as the documentation claims, adds a layer of security protection. It provides integrity protection, authentication, and confidentiality. So if you read the documentation, you think, wow, I just use SSL socket and everything will be good. If your application is based on HTTP, you can just use the HTTPS URL connection, which is also part of the default Java runtime and development kit. And it is basically an HTTP connection class which has support for HTTPS. So far for the theory. In practice, it looks a little bit different. You use one of these classes, and what you get is a really, really obscure error message with a long stack trace of Java or, in this case, it is Apache Harmony classes you never heard about. And the error message itself is already telling. Trust anchor for certification path not found. So some kind of anchor is here. Maybe we're on a ship, and I don't know, maybe the ship couldn't find the right path because GPS is turned off, or I don't know. The conclusion for a developer is certificate verification is just way too secure. It doesn't work out of the box. We try hard, but what we get is gibberish. So usually developers start out by going to Stack Overflow and asking questions like, I'm getting this error, how can I get rid of it? And the answer typically is, yeah, you can do this and that, and after that, certificate verification will be disabled. If you look inside SSL Socket and SSL Engine, which has the two basic building blocks for synchronous and asynchronous communication within Java, use an X509, here we have it again, the public key infrastructure system, trust manager, and the trust manager is used to check certificate validity. It is an interface, and it has one important method, the check server trusted. You give that method a certificate chain. It is a list of certificates from the server, from the certificate authority that signs the server, etc., up to a hopefully trusted root certificate, therefore also the trust path error. And if something is wrong with the certificate, that method throws a certificate exception, which we have seen on the previous slide. Now, how is that X509 trust manager obtained? SSL Socket is never instantiated directly. Instead, it comes from an SSL Socket factory. If you know Java, you know it has to have factories all about it. Because you can't just create an object, you have to have an object factory that creates the objects for you, so you can customize the factory, replace the factory with a custom one. And in our case, that SSL Socket factory is obtained from an SSL Context. The SSL Context is another manager class. And when you initialize this SSL Context, you can actually provide it a list of trust managers to check against. So when we create our own context, we can give it a trust manager. For example, a trust manager that contains this code. this code will just return without doing anything, so it won't throw an exception. It will just accept any certificate you give it. It will accept self-signed certificates. It will accept certificates which are expired. It will accept certificates issued by the NSA. And you just have to add that code into your application, and you don't have to care about security anymore. However, once you do it, of course, your application is susceptible to all kinds of man-in-the-middle and other attacks. So what we get here is an all-or-nothing solution. Either we have very, very secure code which throws up on the first sight of anything which might be wrong, or we have a nothing solution which just accepts everything, which is not ideal for deployments, which is not ideal for development, which is not very ideal at all. Now, we still have the second part of our challenge, which is not the verification of the certificate, but of the host name. We have studied the SSL Socket documentation, and hostname verification is not mentioned in it at all. SSL Socket tells you it is very secure, you don't have to care about anything, so everything is fine. However, in reality, SSL Socket is a transport layer module, and hostname verification is an application layer problem, so it is one layer above in the network stack. And SSL Socket just doesn't do it. What does do it is the HTTPS URL connection, so we can look into it. Of course, HTTPS URL connection is just for HTTPS code. If you are writing code for a different protocol, like, for example, you are writing an email client, or in my case, it was an instant messenger, you somehow need to take the code which is there and adapt it to your own. In HTTPS URL connection, there is a method to set a hostname verifier. Hostname verifier is another interface which verifies a given hostname, provided an SSL session. So you create a session, you connect to a server, and from that server connection, you can obtain the server certificate and match it against the hostname. As opposed to the previous interface, it is a Boolean method that returns true or false. So you have to watch out. You can't just call it and hope it will throw a certification error. It won't. It will just pass. And you have to call that method right after you perform the handshake with the server and before you send any critical data, like your username or password. Yeah, if you want to add that code to your non-HTTPS application, you just call hostname verifier.verify on the hostname and session right after completing the handshake. Don't forget to check the return value. I can't tell that often enough. And the only little challenge we have is where can we get an instance of that hostname verifier? Because you need one to check the hostname. You don't want to write one yourself, or maybe you do. I don't know. So let's look if there's a reference implementation in Java. Unfortunately not. HTTPS URL connection doesn't only allow us to set a hostname verifier, we can also get the default instance of it. And we can add it to our code, and it won't work. It always returns false because HTTPS URL connection internally checks if the hostname matches, and only if it doesn't, it will call the verify method on the hostname verifier. So the code which is part of Java is essentially unusable for us. What a bummer. Let's look into the Secure Socket Extension reference guide, the documentation which was provided by Java developers on how to write a hostname verifier. It must be really easy. I have highlighted the important part. Insert additional matching logic. So you just insert the logic to match the SSL certificate with a host name, and if it is good, you just return true. Sounds easy enough, right? So if we want to write our own hostname verifier, let's look what we have to care about. First, certificates have two different ways to encode a host name. There's a common name, which was the default way for a long time, and later on it was augmented with subject alternative names. It's a list of host names or international domain names or wildcard domain names or IP addresses or IPv6 addresses. You have to correctly handle all these cases. It is a little bit challenging, especially with wildcards. You know, something like star.co.uk could be a certificate for any domain issued in the United Kingdom, which is maybe a little bit too much. So you have to hard code all these special cases in your application. And then people came up with the idea to actually exploit certificates, like embedding null bytes into the command name, and depending on the implementation, that command name will either stop at the embedded null byte or continue to be read, so you can create certificates which look different to different implementations. It is not quite as easy as we first thought. The RFC, which is responsible for it, is 57 pages. And you know, security documentation, it's not that easy for a developer. You really don't want to write it yourself. So let's hope somebody else has written one. And indeed, there is one in the Apache HTTP client library, Apache Harmony. It has a working verifier. For Android developers, it's also good to know that Android embeds Apache's HTTP client as a default system library, and it comes with its own X509 hostname verifier, which is an extension of the hostname verifier we have seen before. So again, the API is turned around. The Apache code is a void method which throws an SSL exception. The original Java code is a code that returns a Boolean value. The Apache has a wrapper method that checks the return value and throws an exception if it is false. And Apache comes with 3 different implementations. There is a strict hostname verifier, which is performing proper hostname verification according to the RFC. It comes with a browser-compatible hostname verifier, which is a little bit less strict with wildcards, where you can have sub-domain wildcards. And there is a allow all hostname verifier, which is not quite as strict. So for our second challenge, the hostname verification, we once again arrived at an all-or-nothing solution. We can have a secure solution. Finally, we have to add a third-party library, but we can get one. And we can either use a strict or an allow all hostname verifier to enable or disable security, basically. In the Java version 7, the developers came up with another interesting API. They created their own X509 extended trust manager. And it is basically an improved version that adds man-in-the-middle attack prevention. So they have extended the interface with a third parameter, a socket or SSL engine, and the check server trusted method then compares the certificate provided by the server with the host name to which we connected, and also throws a certificate exception. So finally, the Java developers came up with an API that is a little bit less insane than previous versions. Of course, Java 7 is not part of the Android runtime, so you have to look for different solutions there. And also, it is not quite as easy to use as just use Java 7 and you'll be fine, because it is not enabled by default. You have to manually enable it when you connect, before you connect. You have to get SSL parameters from the socket. You have to set an endpoint identification algorithm. HTTPS is the one which is there. And it is basically what is done by the HTTPS URL connection and which you can use for most other protocols. So you set these parameters and then you can connect. Of course, you need to supply the host name to the socket somehow so it knows which host name to check against. So when you create the socket, for example, when you have a protocol which is based on start TLS, you start out with a plain socket, issue a magic command like start TLS, and later on your socket is upgraded to a TLS connection. You have to put the host name you connected to into the socket creation. Then you have to set the parameters, and then you are done. So in Java 7 and up, you have, once again, an all-or-nothing solution for hostname and certificate verification. As I mentioned, and Java 7 is not part of the Android API, but the Android developers, they're rather smart, even so I used to bash a bit on them. And they created an SSL certificate socket factory. Once again, a factory, but hey, we are used to it anyway. We are Java developers. And that SSL certificate socket factory is actually pretty well designed. It is available on Android, on all versions of Android, which is a good thing. If you have read about Android fragmentation, it doesn't apply here. It is very well documented. It has warnings in places where you might get around the hostname verification. It tells exactly when hostname verification is performed and when it isn't. And it even comes with a developer mode switch. So you can disable the security. It has a get insecure method to obtain a socket factory which doesn't perform hostname and certificate verification. And you can even do it on a per device basis. If you have a rooted Android phone, you can set a system property and then TLS verification will be developed. However, whenever it is used in an insecure way, you will get a warning in the Android debug log. So it is really, really well designed. It performs certificate and hostname verification. Perfect. It supports development mode. Great. For production, you have at least a choice between all or nothing. So you can have proper security verification, or you can just ignore it. So some Android applications come with a checkbox where you can just disable security, still run TLS, but with susceptible to man-in-the-middle attacks. It is not perfect, but it is already a good start. And it is used by less than 5% of Android applications that have TLS code in them. So everybody uses it. Yeah. From an application point of view, you have usually two different scenarios when you write an application. The first one is you have a hard-coded server which you connect to. For example, you write an application for your company, you have your own company backend servers, you have to connect to these servers. The list of servers, or even the one server name, is hard-coded in your application, and you know it in advance. You know which certificates are deployed on that machine, and you can work with it. If you want to provide additional protection for such an application, the usual approach is to perform certificate pinning. So you pin the server identity to your application binary. This is a very robust approach. You can effectively prevent attacks performed by a root certification authority or by installing additional certificates on your Android device or on your iPhone or on your infrastructure. And it is also working for self-signed or private certification authorities. So it is much more flexible than the previously shown approaches. There is a little difference. There are two approaches possible. You can either pin the server or the CA, which signs the server, public key, and then you are able to exchange the server certificate for that public key. However, certificates usually have an expiration time, so they're created for 1 year or for 2 years, sometimes even up to 5 years. If you use a PIN for a public key, you need to care about expiration time on yourself, or otherwise your PIN will just stay there forever. There are already 2 implementations for pinning the public key. One of them is Android pinning by Moxie Marlingspike, who is a well-known security researcher. The second one has been created just some weeks ago. It is called Java pinning and is maintained by Flowdelix, a developer of the SMAC XMPP library. The other approach is to pin not the public key, but the whole certificate. The problem with it is a little bit less flexible. When you are exchanging the server certificate, because it is going to expire, you also have to update the application code. The benefit of it is all you need is 6 lines of Java code. You don't need an external library. You don't need very much. You start out with a key store file, which you create with a command line from your server certificate, and then you can just add that key file or key store file to your application and load it up into a trust manager factory and provide that factory to the Ssl context. And then all the connections created with that SSL context will be checked for the trust relation to the key store file you provided. So you can add, for example, the root CA, which you are using for signing your server infrastructure into the key store file, or you can add your private certification authority, or you can even add a set of self-signed keys into that certificate key store. And by using that, you are very flexible. You can, for example, have 2 different key store files for development and production, and have a secure implementation that can be using self-signed or official certificates, or even a private certification authority for your own infrastructure. The other scenario is a private cloud application I have mentioned already. If you write an application where the user can enter the host name to connect to, you have to basically care about careless users. So people are doing all kind of stuff with certificates, self-signed, expired, different host names, or a combination of all of these. And to approach such a varying service infrastructure, one approach is to perform trust on first use, or persistence of pseudonymity. If you Google it up, you will end up with a vegetarian music festival. So you have to use the full name. And what it means is basically it stores either the certificate or the public key of the server you connect to on the first connection. And if you connect later on, it will compare the local copy with what the server provided. If there's a change in it, then obviously you were a victim of a man-in-the-middle attack. Now, if you were under attack the first time you connected, of course you will have stored the wrong certificate. So it is not quite ideal. However, at least you will be able to detect that you had been under attack. Now there's a little challenge with the TOFU approach, because the PKI, the public key infrastructure in the internet, has very well-established notion of key and certificate lifetimes. The lifetime of a certificate is encoded into it, and usually when you are creating a new certificate or get a new one issued for you, you can also replace the server key without thinking much about it. With the TOFU approach, you have to stick to the server public key essentially forever. So when you have an application that performs TOFU and the server administrator just replaces the server key, you cannot distinguish that from a man-in-the-middle attack. You need some kind of interactive mechanism where you ask the user, oh, the server key has changed, are you sure you want to connect? You might be victim of a man-in-the-middle attack, or maybe your server administrator just f***ed it up. So you have to show this to the user, and to provide such a mechanism, it is a little bit challenging. In most applications, you have a separation between the user interface and the networking, because networking often blocks, so you have different threads, and you have to create some communication mechanism between the two. Because I had the problem some years ago, I have created the Memorizing Trust Manager for Android. You just replace the System Trust Manager with MTM, and whenever something fishy is happening with a server connection, you just get a pop-up dialog. It is interactive, and the user has the choice to accept and remember the decision, or to abort the connection. On the right, you can see a hostname check. I tried to connect to W3, and the certificate is only valid for the domain itself, so the user is asked about it. It is an open source Android project licensed under MIT. My goal was to improve the overall situation, so use it if you see it fit. And it has a much finer-grained security model than the all-or-nothing approach presented before. However, there's one little challenge. Users of your application usually don't care. They just always click the Always button. They don't read permission dialogues. They don't read server connection dialogues. They just tap OK, get me out of it. So while this is a good approach for security-aware users, it's unfortunately not as suitable for the masses as I thought. And if you want to extend beyond that, we have to consider that users don't care or don't want to care, which is their right to do. And we need to provide some solution which works with careless users. And on the other hand, our root certification authority system, it's not quite perfect. The EFF measured in 2012 that there are over 650 different root CAs which are trusted by the usual clients. So they tested against Windows and they tested against Mozilla Firefox. And any of these over 650 root CAs can issue a certificate for any domain name. So there had been some incidents. Different root CAs, User Trust, DigiNotar, Turk Trust, had been hacked in the last years. And the attackers usually obtain certificates for not quite as important domain names like mail.google.com or yahoo.com. And yeah, it essentially was a big disaster, and Microsoft and Mozilla immediately revoked these certification authorities from their installations. And we need to consider that these were not the last attacks on root CAs, and we need some mechanism to get around it. Certificate pinning is just a partial solution. The problem with pinning is it is not very flexible. You write the certificate or the public key information into your application, you roll it out, and then your server is compromised and you need a new key. By replacing the key on the server, you break all the application installations which are out there because they can't connect anymore. Certificate pinning doesn't scale very well. If you have one server, it's okay. If you have 100 of servers in different co-location centers, if you have TLS terminator servers and load balancers, etc., you have to have a really long list of pins which you maintain in your application. And pinning is very easy to screw up, and then you are there with an application which can connect anymore to your infrastructure, which is not really perfect. So what we need is a way to make pinning more flexible. And there are actually different approaches out there. One of them is TAG, Trust Assertion for Certificate Keys. It has been co-developed by Moxie Marlinspike. And what it basically boils down to is that you have an independent signing key, which acts a little bit like a root CA for all your servers. So you have an independent authority which can sign your server keys. And you provide the certificate of this independent authority with all your certificates that are served to your clients. It is rather short-lived. The maximum lifetime of such a pin is 30 days. So if you break something, it will only be limited in time. However, the signing key or signature is transmitted in-band during the TLS handshake. So it is still possible to perform man-in-the-middle attacks on it. And it has been designed as an extension to the TLS protocol. And as you have seen, the TLS protocol isn't very flexible. People are still using TLS version 1, even though it is deprecated and broken for 8 years now. TAG has been written down as a draft RFC in early 2013, and it expired already. And it doesn't even have a Java implementation available. So it sounds promising, but we can't use it. Another approach is DNS-based authentication of named entities, abbreviated DANE. Here, a different communication mechanism is used to deploy information about the server or the CA identity to the clients. They are stored as DNS records. You can use it for official certificates. You can use it for self-signed certificates. All you have to do is to create a TLS association record in DNS. And ideally, you also should use DNSSEC to secure that entry. Otherwise, it is very easy to fake. The benefit of this is it depends on a different hierarchical security infrastructure. DNSSEC is very strict about who can sign keys for a given domain. So to make a man-in-the-middle attack against DNSSEC, you have to either break into your own DNS infrastructure or into the DNS infrastructure of the target company or into the DNS infrastructure of the top-level domain like .com, or to obtain the root DNSSEC signing key, which is distributed among a bunch of DNS administrators, and they meet every now and then, every some years, to make updates to the root server list. So it is not quite easy to break into. There is a bunch of Java implementations, DNS Java, DNSSEC4J, DNSSEC Java. However, they are all far from ready. They do some DNSSEC validation, but they don't have support for Dane. So they need to be reviewed and to be extended to support that. However, the approach itself is, in my eyes, very promising. And it also allows you to store certificates in DNS. So you could, for example, leverage it for S/MIME without buying expensive certificates for all email addresses you have. Just put them into DNS. Now, we have seen different solutions. If we just use SSLSocket, it isn't very good. It doesn't protect us against man-in-the-middle attacks. We can't use it for private cloud installations because it just throws certificate errors onto us. It's not easy to use in development systems, but it is there. It's the only benefit it has. Apache's HTTP client is a little bit better. It has hostname verification inside, so you can easily man-in-the-middle attack it. However, it is still prone to government-level attacks. Android's SSL certificate socket factory is doing a bit better again because you have a mechanism to switch between development and production mode. If you use certificate pinning with a key store file or with Java pinning, you are pretty good already. However, if you have a private cloud installation with mismatching host names or with self-signed certificates are okay, but if you have an expired certificate, it won't accept it again. Android pinning was designed with the explicit goal to be more secure than the default installation. So it doesn't support self-signed certificates, and it has no provisions for development mode. Memorizing trust management again works very well. However, it relies on the user to ensure that your connection is secure. And if you give it a certificate signed with a different root CA, like created by a government-level attacker, it will fail again. Tag is also an interesting approach. It improves the security against man-in-the-middle attacks, but is not usable for all of the application scenarios. And Dane, using DNSSEC, is really, really promising. The only thing that is missing is somebody who is writing code for it. So the situation isn't perfect, but at least we can do something about it. Thank you very much for your attention, and I'm open for questions.
Mr. Lukas, I enjoyed your talk, man. Fantastic. Okay, great show.
Thank you.
I have a simple question for you, very, very simple. In your presentation, you mentioned root certificate is flawed.
Yeah.
Independent authority signing the certificate is a real issue, so-called independent authority.
Yeah.
Okay, VeriSign and whatnot, right?
Mm-hmm.
So if you remove these authorities, replace with something totally different, do you think we have a solution here? Because I don't trust any of the independent authorities.
If you don't trust any of the authorities, you need some other way to ensure that the server is authentic, and you need to trust somebody. You have to trust DNSSEC in the case of Dane. You have to trust maybe a limited set of authorities, which you have chosen yourself for your application. So you can say, I only trust VeriSign, but I don't trust TurkTrust, or I don't trust the Chinese NIC, the Network Organization of China. You can choose the set of trusted root authorities. But essentially, TLS doesn't provide a mechanism to limit who is able to sign which domain names. So any of the trusted certification authorities can sign any domain, and you have to trust all of them. There are approaches which go beyond that. For example, there is an approach by Google to make certificate issuing publicly auditable. They add a public log of all certificates issued, and you have a server record which you send to the client so it can validate the server name is actually in the log. And then the owner of the domain can check the log if somebody else got a certificate for his domain name. So there are approaches out there to improve the situation, but there's no ultimate solution for it.
Hi. Just a comment on tag and key pinning in general. So from the IETF side, tag died. Mm-hmm. It's really dead, mainly because of Google. They didn't like it. And they just invented their own tag, which is only limited to HTTP. It's HPKP. HTTP key pinning, which has become a standard like 2 weeks ago.
Okay.
As for Dane, Google also doesn't like Dane, so I don't see it getting deployed.
Bummer.
And the Java stuff was awful, but it's not as bad as using OpenSSL API.
Yeah.
Hi, so thanks for the nice overview. I saw one thing, you claimed that Dane would be immune to governmental attacks. However, I was wondering why that would be, because you're moving basically the trust architecture from TLS over to the domain name system, but on the very top of this DNSSEC system, so to speak, there are these root keys that are distributed at various providers, just I think Verizon that is, for instance. Oh, all right. So, yeah, basically, the idea behind this is these root keys could be compromised by the governments. Hence, Dane wouldn't provide, the amount of protection against governmental adversaries in this case.
I would say that you have limited access for government. So it boils down to the United States government being able to compromise the system and not the government of any third world country.
Okay. Aren't there efforts to distribute the DNS system across multiple nations? Wouldn't that also affect the distribution of the root keys?
As far as I understood it, the DNSSEC root key is actually only available when all of the persons having parts of the key meet in person in one place, so they can make changes. Okay, if you know it better, please. I'm not a DNSSEC expert, sorry.
Well, I had to be a bit. There are actually two sets of root keys in the DNSSEC. One is the zone signing key, one is the key signing key, because DNSSEC usually has two keys for every zone. So the key signing key of the root is the one that's distributed and not in one place. Actually, it's not true. It's on smart cards, but the recovery key is distributed amongst trusted persons across the world. But the daily signing of the daily updates of the root zone is done by a zone signing key, and that's actually in the hands of, I think, IANA or VeriSign as the root zone primarily operator, the one who runs the rootservers.net. So it's only the key signing key. That's the key that everybody stores in their trust chains on their PCs. That's the one that's with the high level of security, not the daily operational update zone signing key.
Thanks for your nice talk. I got a question about certification revocation. After Heartbleed, everybody has learned that the revocation list won't scale very well, and there was a move to OCSP. Did you have any experience how that Java libraries can handle OCSP? And maybe furthermore, if there is also in support for OCSP stapling right now?
I haven't encountered any working OCSP implementation within of that code. I'm pretty sure that it is just disabled or isn't available at all, because typically certificate revocation isn't working very well. It doesn't scale, and you have to block your connection until you get positive from the server. It is better with OCSP stapling, but as an attacker, you have still ways to get around it, even so for a limited time.
Thank you.
So, some more questions? No, then thank you. Oh, okay.
Did you check the issues you encounter when using IDN domains, so domains with foreign keys. Because as far as I remember, the encodings in X509 are different than the encodings on the NES layer. Any fun with that? Any experience with that?
I haven't looked into the details because basically I have just plugged in the different hostname verifiers that were available on the system instead of writing that on my own.
And they do work with umlaut domains and other interesting Arabic, Chinese domain names and that stuff.
I'm not quite sure. I think that you have to encode the Punycode version in the certificate.
I do not know.
Using Unicode certificates is probably active fuzzing. Don't do it.
So, okay.
Thank you very much.
No more questions? Thanks.